Hi, I am Sanjay Singha and in this short demo video, I will explain doping and ion implantation techniques, two fundamental processes used in semiconductor fabrication. Doping. Doping is the process of addition of impurities into a pure semiconductor to change its electrical properties. The main aim of the doping is to increase the number of free electrons or holes in the materials. The impurities which are added to these pure semiconductor materials are also called dopants. Dopants are of two types, N-type and P-type. N-type dopants are those which donates electrons and P-type dopants are those which accepts electrons or create holes. The example of N-type dopants are phosphorus, arsenic, antimony, and the examples of P-type dopants are boron, gallium, indium, etc. The two key methods that are used for doping are diffusion and ion implantation. Now, let's look at diffusion, which was the primary doping method until early 1970s. In this technique, dopant atoms are deposited onto or near the surface of the semiconductor wafer. This is done using dopant gases like PH3 or B2H6 or even through doped oxide layers. The wafer is then heated to a high temperature, typically between 900 degrees Celsius to 1100 degrees Celsius, causing the dopant atom to gradually diffuse into the silicon. The resulting dopant profile shows a monotonically decrease in concentration with depth. In other words, the highest concentration is at the surface and its decrease smoothly deeper into the material. The distribution is mainly controlled by temperature and diffusion time. Diffusion is specially suitable for forming deep junctions such as twin tube wells in CMOS technology. This slide gives a visual representation of the Gaussian profile explained in diffusion. Here, as the depth increases, the concentration of dopant decreases. Now, let's talk about ion implantation, a highly precise doping technique that became widely adopted since the early 1970s. In this method, dopant atoms are first ionized and then accelerated using high energy ion beam. These ions are implanted into the semiconductor material at very controlled depth, allowing for excellent precision. However, this process caused some lattice damage, so a post-implantation annealing step is required to repair the crystal structure and activate the dopants. Unlike diffusion, the dopant profile here shows a peak concentration beneath the surface, often with a bell-shaped distribution. The depth spread of the profile are determined by the ion masses and implantation energy. This makes ion implantation ideal for creating shallow junctions like the source drain region in MOSFET, where accuracy and control are critical. Overall, the ion implantation is an essential tool in modern semiconductor fabrication. Here, in this slide, you can visually see the Gaussian profile of ion implantation technique. It shows a bell-shaped structure. Thank you.